All right, so strap yourselves in, folks, because today we're diving deep into something that I think is going to really resonate with you as a philosopher, and that's how different theories in physics actually relate to each other.
It's called intertheory relations,
Right.
and yeah, it gets pretty philosophically juicy.
I bet. It's not as simple as like, one theory being right and then another one being tossed in the trash, right?
No, definitely not. It's more like this really intricate web of connections between them, and we see things like reduction, equivalence, dualities, just a whole network of how these theories can actually interact.
Okay, so there's a lot to unpack there, but for this deep dive, we're going to zero in on the idea of reduction. And as a philosopher, you've probably come across this concept before.
Right.
It's about how one theory can be explained or even, absorbed by another theory,
Yeah.
maybe a more fundamental theory.
Absolutely. And a classic example that might resonate with you is how physicists in the 19th century, like Clausius and Boltzmann, actually saw atomic theory as the key to really understanding the second law of thermodynamics. And it's not about saying that the second law was wrong, it was about finding this deeper explanation for why it works so well.
So we're not just talking about replacing theories, but we're talking about finding those deeper connections and explanations. So it's like building this more complete, intricate picture of the universe.
Yeah.
But, and here's the thing, what does reduction even mean? Philosophers have been like really wrestling with that question forever.
Oh yeah, and that's where the fun starts, right? So one of the major figures in this whole debate is Ernest Nagel, a philosopher who proposed a pretty influential model of reduction, and he argued that it's all about this idea of deducing one theory from another, like kind of fitting puzzle pieces together.
Right, and that makes intuitive sense, right?
Yeah.
If our reducing theory is true, then the reduced theory must also be true, at least under the right conditions. Philosophers love that kind of certainty.
Of course. But there's a catch.
Oh,
Even some really seemingly straightforward examples like Galileo's law of falling bodies and Newton's laws of motion don't fit perfectly into this deduction model.
oh, really?
Yeah, we often need to use approximations, and that makes things, well, a bit messier.
So it's not as cut and dry as we might hope.
Right.
So what are some of the other models that philosophers have, put forward?
Well, Kemeny and Oppenheim, they came along and sort of shifted the focus a bit. They said that reduction is really about whether both theories make the same predictions about what we observe.
So it's less about the underlying reality and more about the empirical results.
You got it. But of course, this approach has its critics too. Some would argue that it's a bit too weak, that it doesn't give us the satisfying connection between the theories themselves, this feeling that the world really hangs together in a deep way.
Right. It's missing that, I guess, that ontological glue that we as philosophers, often want.
Right.
So where does that leave us?
Well, then there's the GNS model. This is the generalized Nagel-Schaffner model, which actually tries to refine Nagel's ideas. It acknowledges that we need some wiggle room, that sometimes we need to tweak things a bit to make those pieces fit. So think of it like this Maxwell's theory of electromagnetism. It didn't completely discard the older theory of physical optics, right?
Right.
It corrected it and refined it, leading to these more accurate predictions while still preserving a lot of those core insights.
That's a great example. I mean, that speaks to how scientific knowledge progresses,
Yeah.
right? We're building on and refining what came before
Yeah.
rather than just like throwing it out the window.
Exactly. And that leads us to this other fascinating type of reduction, and it's one that physicists use quite often, which is limiting reduction.
Limiting reduction.
And this is about getting one theory from another one through these mathematical limits.
Okay, I think I'm following you. Can you give me like a concrete example to help me understand?
Yeah, sure. So imagine that you're kind of zooming out from the universe, and the speed of light becomes effectively infinite. What emerges is a picture that looks very much like Newtonian physics. So it's like Newtonian physics is this simplified version of relativity that works well under certain conditions.
So we're not saying that Newtonian physics is wrong, just that it's a special case, like a limited view of this more fundamental reality.
Exactly. And this ties into all these debates about emergence that philosophers, you guys grapple with. But here's where things get even more interesting. There are these things called singular limits that can really throw a wrench into this whole reductionist picture. Sometimes the behavior at the limit is fundamentally different from what we see in that zoomed-in theory. It's not just a smooth continuation.
It's like those optical illusions
Mhm.
where what you see at first glance, that's not the whole story.
Exactly. A perfect analogy. So think about phase transitions in thermodynamics. The sudden jump between states like water turning into ice that only appears at the limit, at infinity. And that raises all these tricky questions about how something that's infinite can really explain something we observe in this finite world.
That's definitely a head-scratcher. But I'm guessing there are counter-arguments to this idea of singular limit.
Oh, of course. There's always another side to the coin. So some argue that even finite systems show behavior that's almost like the limit. It's like getting closer and closer to that optical illusion, even if you never quite reach the point where it completely flips, right?
Yeah.
But then that raises another question. How different does different have to be for us to actually call it true emergence?
Yeah, that is the question. So we've covered a lot of ground age-old limits emergence. It seems like this reduction thing is a lot more complicated than it appears at first glance. What other perspectives should we consider here?
Well, we can't forget about the structuralist approach, which takes a different view of theories altogether. So instead of focusing on statements, it emphasizes models, the structures that represent relationships between concepts.
Ah, so it's less about specific details and more about the underlying framework. That sounds very appealing from a philosophical standpoint.
Exactly. And this gives us a way to actually handle approximative reduction, which is something other models have really struggled with. It's a more rigorous way to capture this messy, nuanced reality of physics.
Right.
But of course, there's always a challenge. So the question is, does it capture all meaningful reduction in physics? And well, the debate continues.
Sensing a theme here. In philosophy and physics, the debates never really end, do they?
That's what keeps things interesting, right? But before we go too far, there's one more concept we need to touch on: supervenience. This is a big one for philosophers.
Right. Supervenience. It's about how properties at different levels relate to each other, right? Does the higher level depend on the lower level? And if so, how?
Exactly. And the type of dependence really matters here. So we talk about strong versus weak supervenience.
Okay.
Strong supervenience might get us closer to reduction, but even then, there are these examples in physics that make things really complicated.
So even defining the relationship between those levels is tricky business. It's fascinating how reduction in physics can lead us into these deep philosophical waters.
It's all connected, isn't it? And speaking of tricky concepts, we've kind of danced around emergence quite a bit. Is it just failed reduction, or is there something more to it, something truly novel? Now that's the million-dollar question, right? And this is where recent thinking in philosophy of physics gets really interesting. Emergence and reduction, they might actually be compatible.
Wait, really? I thought those two ideas were like on opposite sides of the philosophical battle lines, like oil and water.
Well, it's a common misconception. Think of it like this. Emergence is about the relationship between scales, how things behave differently at different levels of zoom. Reduction, on the other hand, that's about the relationship between theories, how we connect those different levels of explanation. So they're kind of approaching the problem from these different angles.
Okay, so it's not necessarily a case of one being right and the other wrong, but more about understanding how they both contribute to our understanding of the universe.
Exactly. And this is where this idea of weak versus strong emergence comes into play. So we're not denying that fundamental physics underpins everything, but we're also open to the idea that new and interesting things can happen when you kind of zoom out, when you consider the collective behavior of all those fundamental building blocks.
It's like saying that the laws of physics are like the sheet music, but the
Yeah.
symphony itself is something more, something that emerges from the complex interplay of all those notes.
Yeah, you're getting it. And this idea of different levels of description working together is also at the heart of another really important area of physics effective field theories, or EFTs. Have you come across those at all in your philosophical explorations?
I can't say I have.
Yeah.
What are EFTs and how do they connect to all this discussion of reduction and emergence?
Well, EFTs are kind of like these specialized tools for specific situations. They capture what's relevant at a particular scale without needing to know all the intricate details of this underlying more fundamental theory. It's like if you think about using Newtonian physics to predict how a ball will roll down a hill, you don't need to know the precise arrangement of every single atom in the ball or the hill to get a pretty good prediction.
So we're saying that different levels of explanation can be valid, even if they don't all boil down to the same fundamental principles. It's like having different lenses for looking at the universe.
Precisely. And this really challenges the idea of this neat hierarchical picture of science where everything neatly reduces down to one single fundamental theory. It's more like a network of these interconnected theories, each with their strengths and limitations.
So instead of a ladder, it's more like a web with connections going in all sorts of directions.
A beautiful image, and this web-like interconnectedness becomes even more apparent when we start to think about multi-scale modeling.
Okay, multi-scale modeling. Now that sounds interesting. Tell me more.
Well, as the name suggests, it comes into play when scientists are dealing with systems that involve processes happening at these vastly different scales. Think about climate change, for example. You've got these global atmospheric patterns interacting with local weather phenomena, all while being influenced by these microscopic processes happening at the molecular level.
So it's not just about understanding each level in isolation, but it's about seeing how they all fit together, how they influence each other.
Right. And this poses a real challenge for traditional reductionist thinking. If we need to consider multiple scales to fully understand a phenomenon, does that mean reduction to a single fundamental level is insufficient?
It's like trying to explain the beauty of a symphony by only analyzing the individual notes played by each instrument. You miss the bigger picture, the way those notes all come together to create something greater than the sum of their parts.
A perfect analogy, and it brings us right back to those questions about emergence and reduction. Are these higher level emergent properties truly novel, or can they ultimately be reduced to the interactions of their constituent parts?
It seems like we're back to that idea of different lenses, right?
Yeah.
Maybe reductionism is still valid, but we need to recognize that it's not the only lens we need to make sense of the universe.
That's a perspective many philosophers of science are exploring these days. Some argue that even in these multi-scale models, we can still trace the causal chains back to fundamental physics. It might be incredibly complex, but the idea is that everything ultimately boils down to the interactions of those fundamental entities.
So it's like saying that the symphony's beauty, while emerging from the individual notes, can still be explained by understanding how those notes combine and interact according to the laws of acoustics and harmony.
Exactly. But others argue that multi-scale modeling really highlights the limitations of this traditional reductionism. They would say that these higher level phenomena have their own unique causal powers that can't be fully captured by just analyzing the lower level details.
So the symphony's beauty is more than just the sum of its parts. It's this new, emergent property that arises from the complex interplay of those parts, but can't be reduced to them entirely. Sounds like this debate is going to keep philosophers and physicists busy for a long time to come.
It certainly will, and it's a debate that goes to the heart of how we understand the relationship between different levels of reality and the very nature of scientific explanation.
This has been incredibly illuminating. I'm starting to see how inter-theory relations in physics are so much more than just equations and derivations. They touch upon some of the most fundamental questions about the nature of reality and how we understand it. Questions that philosophers have been grappling with for centuries. It really has been quite a journey, hasn't it? We started by looking at reduction, this idea of connecting theories and finding those deeper explanations. But I think as we've explored these different models and approaches, it's become clear that there's so much more to this whole story, right?
Yeah.
It's not just about fitting those puzzle pieces together. It's about understanding that complex interplay between different levels of description, the emergence of new properties, and really even the very nature of a scientific explanation itself.
And for you as a philosopher, I think these ideas have implications that extend far beyond just the realm of physics. They really challenge our understanding of knowledge, causality, and the very structure of reality.
Yeah, absolutely. We've talked about Nagel, limits, emergence, supervenience, EFTs, multi-scale modeling. It's like we've opened up this whole Pandora's box of these philosophical questions.
And that's the beauty of it all, right? These questions don't really have easy answers, and I think they invite us to keep questioning, to keep exploring, and keep pushing the boundaries of what we understand.
It's like we've been climbing this mountain of knowledge. And just when we think we've reached the summit, we realize that there's a whole new range of mountains stretching out in front of us.
A perfect metaphor. And that brings us to this question that has fascinated both philosophers and physicists for centuries, which is whether the world actually truly bottoms out at some fundamental level.
Right, the idea of a theory of everything, that ultimate reductionist dream.
Yeah.
But as we've seen, even if such a theory exists, it might not be the end of the story.
Exactly. Think back to those effective field theories we were talking about earlier. They suggest that even if we have a theory that explains everything at that most fundamental level, we're still going to need these different tools, different lenses to understand the universe at all these different scales.
So it's not about finding that one true explanation, but it's about recognizing the validity of those multiple perspectives, those multiple levels of description.
That's a really powerful insight, and it challenges us to think about reduction in this much more nuanced way. Maybe it's not about finding that one ultimate set of building blocks. but rather understanding the intricate web of connections between all those different levels of reality.
It's like saying that the universe is more like this endless fractal with complexity emerging at every scale.
Mhm.
Even if reduction holds true in some sense, that journey of discovery, it might never truly end.
And what a beautiful journey it is. So, to our listener who has joined us on this deep dive into the philosophical heart of physics, I just want to leave you with this thought. Embrace the complexity, embrace the mystery, and keep asking those big questions. That's what makes this whole pursuit of knowledge so endlessly rewarding.
Couldn't have said it better myself. Until next time, keep exploring and keep diving deep.